Welcome to the next tutorial in three-phase induction motors. In this tutorial, we are going to solve few problems on power calculation. So the first problem goes like this. If a 440 volt three-phase 50 hertz star connected induction motor has a full load speed of 1425 rpm. So the speed of the rotor at the full load condition is 1425. The rotor has an impedance of 0.4 plus J4. So here we have been given the impedance. It means the real part is basically the resistance and the imaginary part is basically the reactance. The rotor to stator turns ratio is given to be 0.8. So when we need to find the transformation ratio, then we have to divide the rotor to stator turns ratio, which is equal to 0.8. Now we have to calculate the full load torque, rotor current, full load rotor copper loss, power output if the windage and the friction losses amount to 500 watt. So this is the total loss due to windage and friction losses. The maximum torque and the speed at which it occurs. So what is the speed at which the maximum torque occurs? The starting current and the starting torque. So these particular parameters we need to calculate for the three-phase induction motor. So let us see the solution. So the first step is to calculate the synchronous speed. So synchronous speed is basically given by the formula 120 into frequency divided by the number of poles. So here the frequency is 50 Hz and the number of poles is 4. So we are getting 1500 RPM. We know that in induction motor the formulas have been derived for the revolution per second instead of RPM. So it is better to change the unit from RPM to RPS here itself. So 1500 RPM is correspondingly to 25 revolution per second. Now we have to calculate the slip. So slip is basically what is the change in the speed relative to the rotor and the stator. So we have seen that the value of the rotor speed is given Nr. So if we subtract Ns minus Nr, because Ns will always be greater than Nr, divided by Ns, we will get a value of the slip. So the change in the speed between the stator magnetic field and the rotor is 75 rpm, whereas the 1500 rpm is basically the slip, basically the synchronous speed. So we get a slip of 0.05, which is dimensionless. Now the induced EMF E1 in the stator is basically 440, that is the line voltage divided by root 3, because we have to convert it into phase voltage. So we get a value 254 volt. Now the full load torque equation is given by 3 by 2 pi ns. So we have been given the value of ns as 25 rps, so that we have substitute, and then we have to multiply the value of, this is the total impedance, z square. So z square is basically r square plus slip time x whole square. So we have to get the values of the rotor resistance. So this is your rotor resistance, and what is the value of the slip S into E2. Now E2 is basically the rotor induced EMF, so which we can get it from the value of the transformation ratio K in multiplied with E1. So E1 we are getting as 254, so we have to multiply that with K times, that is the transformation ratio, which is a rotor by stator, given by 0.8. So we get the value of the torque at the full load condition is 78.87 and the unit is Newton meter. Now the current, rotor current. So the current we have to derive under the running condition IR. So S into E2 in the numerator is basically the voltage which is there under the running condition, and in the denominator we have the total impedance. So impedance is basically rotor resistance square plus slip time the standstill reactance square. Now the value of E2 can be written in terms of E1, that is K into E1, and after substituting the appropriate values of the slip, the rotor induced EMF, the E1, R2, X2 and the slip, we get the rotor current as 22.73 ampere. So this is the rotor current which we have got it. So what is the total copper loss? So total copper loss is basically 3 times the current square multiplied with the rotor resistance. So here we will be having R2. Now 3 is multiplied because we have to calculate the total copper loss which is corresponding to 3 phase. So we know that I square R is basically the copper loss in single phase, so multiplied with 3 times, and the current is basically under the running condition, and to R2 is the rotor resistance. So we get the value 620 watt as the total copper loss. Now the value of the mechanical power PM, gross mechanical power, is equal to 2 pi n into T, because we know that power is equal to omega into torque. So omega can be written as 2 pi n and torque value we have already calculated. Now we have to convert this speed into revolution per second, and the torque we have got at 78.87 Newton meter. So we get the power as 11745 watt. So, and the power output is basically, so whatever the output power we have is the gross mechanical power minus the total losses in the windage and the friction, which is given in the problem as 500 watt, and 11745 watt is basically the value of PM. So we get the output power as 11 to 45 watt. Now the maximum torque condition, we know that when rotor resistance is equal to slip time the rotor reactance. So here we get the maximum torque. So slip corresponding to the maximum torque can be obtained is the rotor resistance by the rotor reactance, or in the standstill condition. So we get the value as 0.1. Then what is the maximum torque? So we have to substitute the value of the slip as 0.1 in the particular equation of the torque that we have seen in the previous also, keeping other quantities, that is the rotor resistance and the rotor reactance constant. We get 98.5 Newton meter as the maximum torque corresponding to slip s equal to 0.1. Now, since slip is 0.1, it means that the slip speed, that is the rotor speed, is basically S into Ns. S into Ns is the slip speed. So 0.1 is basically the slip into the synchronous speed of the machine. So we get a value 150 RPM as the slip speed. That is the relative speed. So what is the speed for the maximum torque? So speed for the maximum torque, that is we need to find the value of Nr. So it is equal to Ns, that is 1500 RPM, minus the slip speed, which is 150 RPM. So we get 1350 RPM as the speed when the machine is giving the maximum torque. Now we can find the starting current. So starting current is basically whatever the voltage we have divided by the impedance. We know that during the starting the value of the slip is 1. So we can substitute the slip as 1, and the value of the rotor induced EMF E2 is equal to K times E1, where K is the transformation ratio rotor by stator turns ratio, and E1 is basically the induced EMF on the stator side per phase, so it is equal to 254, and the rotor resistance and reactance we have given. So under the starting condition we get 50.5 ampere as the starting current. So the starting torque, then at the starting we have the slip equal to 1, and whatever the formula we have put it in the torque max equation, the same type of formula we can put in the torque starting. Here the value of the slip will be 1, because here we have 0.1 for the maximum torque. So at the starting torque you have to put the value of the slip as 1. Then rotor resistance and reactances will be there. Only thing is that slip will be 1, and for that we get the starting torque as 19.5 Newton meter. So we can see that the maximum torque is at 98.5 Newton meter and the starting torque is 19.5 Newton meter. So let us see the second problem then. So in the second problem you have a 100 kilowatt 3300 volt 50 hertz 3 phase star connected induction motor whose synchronous speed is given to be 1500 rpm. So here one thing we have to observe is that whatever the voltage is being given for a three-phase system, this is the line voltage, and the power that is being given is basically the three-phase, the total power that is being given to the load. So this is the total full load condition, whatever the power given to the three-phase load. So synchronous speed is 500 rpm, and the full load sleep, so sleep corresponding to full load is 1.8%, and the full load power factor is 0.85. Now different losses we have been given, that stator copper loss is 2440 watt, iron loss is 3500 watt, and rotational losses is 1200 watt. So rotational losses means the friction and the windage losses. We have to calculate the rotor copper loss, line current, and the full load efficiency. So what is the rotor copper loss? So you have to determine what is the value of PCU, the line current that is flowing in the system, three-phase induction motor, and the full load efficiency of the motor. So let us see the solution. First, the gross mechanical power PM is basically the total output power plus the rotational losses. So we have been given the output power as 100 kilowatt and the rotational losses is 1.2 kilowatt. So we getting the total mechanical power as 1.2 kilowatt. So rotor copper loss formula in terms of the slip is basically slip 1 minus S into PM. So here we have determined what is the value of the rotor gross mechanical power, and we have to find at a particular slip what is the rotor copper loss. So that values of slip and the gross mechanical power we substitute and find the rotor copper loss as 1.855 kilowatt. Then the rotor input. So rotor input, we know that this is the rotor. Then we have the input which is given as P2, and this is the mechanical gross power PM. So we have the rotor copper loss PCU. So P2, that is the input, is basically the output PM plus the total loss, that is the rotor copper loss. PM, that is the gross mechanical power, has been obtained as 101.2, and the rotor copper loss is given as 1.855 kilowatt, which we have obtained. Hence the rotor input power is 103.055 kilowatt. So the stator input power, now we know that this is your stator and this is your rotor. So stator will be having a power P1, and the PM, which is the output, P2, which is the output of the stator, will be the input of the rotor. So here in the stator you will be having a loss which is stator copper loss and the iron loss. So the losses in the stator is basically stator copper loss and the iron loss, and P2 is the output of the stator, which is the input of the rotor. So P2 we have obtained 103.055, which is the rotor input power, plus the total amount of losses in the stator, which is the copper loss and the iron loss. So if we add, we find the stator input power as 108.995 kilowatt. Hence the line current, now we can find from the formula that the real power P is equal to root 3 times the line voltage into line current into the power factor cos phi. So the power, this is the stator input power, is basically the three-phase power 108.995. So root 3 times the line voltage, we have 3300. Line current we have to find, and the power factor is 0.85. So we find the line current to be 22.4 ampere. Now the entire flow in the motor then is as such. So we have the stator input first, which is 108.995 watt. The some amount of power is going in the stator copper and the iron losses, which is 5940 watt. Then we have the rotor input, which is the output of the stator. So stator output become the rotor input, that is 103.055 watt. Some amount of rotor copper loss is there, which is 1855 watt. The subtraction of the rotor input by rotor copper loss, we get the gross mechanical power developed. So this is equal to your PM, and this is your P2. So here you have the rotor copper loss PCU. So the rotational losses, if we subtract, that is 1200 watt, we get the output power, which is the shaft power. So this is the actual power that is being used by the system given by the motor. So it is equal to 100 kilowatt. So we can see that how the flow of the power is there from the input, that is the stator, and then it goes to the rotor, and then it goes to the load. So stator to rotor power flow and rotor to load power flow with different losses: stator copper loss, iron loss, rotor copper loss, and then we have the rotational losses, and then it goes to the load. Then the full load efficiency we can determine as the total output power by the total input power. So we see the output power is 100 kilowatt and the input power is 108,995 watt. So if we divide the output power by input power, we get an efficiency of 91.7%. So here the efficiency of this induction motor problem is 91.7%. So in this tutorial we have solved few problems on power calculation, and we have seen what are the different type of losses that can take place in induction motor in the stator as well as in the rotor. Thank you for now.